Welcome to all. Till now we have solved the problems on elimination approach method. So now we are moving to the next type of boundary condition method, that is known as penalty approach method. This is also one of, as per the examination, it is also very important. We'll see how this boundary condition going to be approached by using this method, and we'll solve the problems on this. So as the name indicate, penalty means some kind of compensations. So some kind of compensation we are going to adding. So it is a type of boundary conditions method. In this method, adding penalty. So I told you, right, adding some kind of compensation. So here we are adding that compensation, that is called C, that is called as C, to the corresponding end conditions of the structure. What is the boundary condition they given? To correspond to the boundary conditions of the end condition, we are going to adding with respect to the particular nodes. Which node we are going to apply the boundary condition? We are going to apply this C value there in global, that is in the global stiffness matrix, and also we are going to add in a force vector matrix. So in a which is the global stiffness matrix and force vector in a equilibrium equation. What is equilibrium equation? We know that, right? We know that, right? KQ is equal to F. So in the stiffness matrix as well as force vector, we are going to add the penalty called as C. So what is C? That C is nothing but maximum of Kij into 10 raised to 8. That is nothing but maximum value of stiffness. Maximum value of where Kij is the stiffness, maximum stiffness value, which is obtained in the global stiffness matrix. In a global stiffness matrix, once we find out the global stiffness matrix, what is the maximum value will be there, like K13, K12, K21, K22, K23, like that. Out of that, which is the maximum, that value we need to multiply into 10 raised to 4. That is called as C. Let's take an example of this. So this is a bar, it is fixed, it's subject to axial load. Now suppose for this the equilibrium equation is like this: K11, K12, K13, K21, K22, K31, K32, K13. So Q1, Q2, Q3, F1, F3. Now if you apply the penalty approach, see now node 1 is fixed, right? So therefore at node 1 is nothing but K11. We are going to add the C in the stiffness, as well as this C will be added in a force vector also, that is F1 plus C into A1. So what is A1? A1 is nothing but free displacement. A1 is nothing but free displacement, or some generally we can call it as AI, where I is the node number. Suppose here you can see there is no free displacement, right? AI is become 0, A1 become 0. Here free displacement is there. So like that, we need to add what is the force given plus C times of that free displacement. If free displacement not there, then that is become 0. And also here reactions we are going to calculating like this. That is, reaction is minus C QI AI in general, minus C into QI minus AI, where Q is the nodal displacement, A is the free displacement, and C is the penalty, where I is the number of nodes. Suppose with respect to this example, here suppose at node 1, therefore R1 is equal to C into Q1 minus A1. Therefore A1 anyway 0, that is become only minus C1 minus C into Q1. So this is about the penalty approach method theory. So this is the best way I can explain you. In textbook they are given in a spring method, taken spring and they are explained derived the equation. So we don't want those derivations, okay? So it's the best way I explained you. So please go through this, and when you're going to solve the problem, concept will be clear. We'll see how to solve the problem on this. So that is known as penalty approach. So usually in a examination, they are ask you directly solve the they may clearly mention in the problem that using a penalty approach only you have to solve the problem. If they are not given, you can solve by um, either by Gauss elimination method, or it may be by penalty. But if they mention particularly about which type of boundary condition you have to solve, then you have to solve that. So we'll take an examination problem. So the bar shown in figure, that is a compound bar loaded as shown in figure, determine nodal displacement, stress and reactions. Take Young's modulus for the steel and copper is 200 GPa and 100 GPa respectively. Steel is 200 and copper is 100 GPa. So this is the composite bar made up of two different material, one is steel and another is copper, having a different cross section. So and is 60 mm dia and 40 mm dia, and at the center it is subject to a load of 100 kN. It's having length of 800 and 500. See, this is the same kind of problem. We already solved this type of problem in a using elimination approach method. Same problem only we are going to solve in a penalty approach. Therefore, here up to the step up to boundary condition method, the steps are same, no changes. So only in the applying the boundary condition the problem will be changed. So that's why we are taking the same problem now. We will solve this by using a penalty approach. We'll see now. Let's write the given data. Let's divide into two sections, 1 and 2. L1 become 800, A1 become pi d square by 4, that is 2827.4 mm square. A2 is pi d square by 4, that is 1256.63 mm square. E1 is 200 GPa, convert into Newton per mm square, multiply by 10 raised to 3. Similarly, E2 is 100 GPa, 100 into 10 raised to 3. We need to find first question, nodal displacement, stresses in each element, and reactions. So first step, as we know that first step is we need to write a FEA model. We divide into two elements having a corresponding nodes are Q1, Q2, Q3. Sorry, nodes are 1, 2, 3 and nodal displacements are Q1, Q2 and Q3. So the second step is we know that we need to find the elemental stiffness individually. For element 1, K1, A1, E1 by L1, 1 minus 1 minus 1. So if you substitute all the values of A1, E1, L1 and then if you calculate this, that is become 7.07 into 10 raised to 5. Keep 10 raised to 5 outside and multiply by 7.07 inside. Similarly, K2 become E2 L2 by A2 E2 by L2, that is 2.513 into 10 raised to 5. We taken inside the 2.513 and 10 raised to 5 keep outside. Now we need to assemble this global stiffness matrix, that is K1 plus K2. Then if you add it, you get like this. So now we need to find, next step is global displacement vector Q1, Q2, Q3 and global force vector F1, F2, F3, that is F1 is 0, F3 also 0. At F2, at node number 2, the load is acting, that is 100 into 10 raised to 3 Newton. Now we need to write a equilibrium equation. This KQ is equal to F. Up to here is steps is same. Now here the changes. Please observe carefully. We need to apply the boundary condition using penalty method. Since node 1 and node 3 is fixed, apply penalty C in a stiffness. So here node 1 is fixed, node 3 also fixed. Therefore we need to apply a penalty C value in a stiffness matrix at node 1 and node 2 as well as global stiffness matrix. So this C we need to find by considering the largest stiffness value in the global stiffness matrix, which is the largest stiffness value here. So that is 9.583 into 10 raised to 5. 9.583. Don't take only this outside the what is the value we taken 10 power, that also you need to consider. 9.583 into 10 power 5, that is K22 value. Therefore C becomes maximum stiffness value into 10 raised to 4, that is 9.583 into 10 raised to 5 into 10 raised to 4, it is become 10 raised to 9. Now also we need to apply the C in a global force vector. So therefore at node 1 and 3, so node 1 become F1 plus CA1, F3 plus CA3. Here there is no a1 and a1 a3 becomes 0. Why? Because it is fixed. The bar is not freely moving, therefore a1 a3 become both are 0. Keep this in mind, this is very important. a1 a3 are 0 because no free displacement at the nodes. So therefore now the modified equilibrium equation become, now where do you need to add the c now? At k11 and k13, node 1 and node 3, that is k11 and k33, plus c we need to add also the global force vector become f1 plus ca1, f3 plus ca3. Now we need to substitute the c value, that c value 9.53 into 10 raised to 9. You already 10 raised to 5 it is outside there, therefore in that we take only 10 raised to 5 comma outside, therefore remaining will be 10 raised to 4 into 9.583 plus 7.07. Similarly here, so here anyway f1 is 0, a3 a1 also 0, therefore total term becomes 0. Here f3 also 0, a3 also 0, therefore again the total term becomes 0. So if you add these two, this is the value you will get. Now you can able to solve this by simultaneous equation. So I shown the simplification. So 10 raised to 5 you take on this side, so this into q1 minus 7.0 into q2 equal to 0 by 10 raised to 5 0 minus 7.07 into q1 plus 9.53 into q2 minus 2.513 into q3 equal to 100 into 10 raised to 3 divided by 10 raised to 5. So the 100 into 10 raised to 5 nothing but 10 raised to 5 cancels, that is become 1. Similarly 0 minus 2.513 into q2 plus 9.583 into 10 raised to 5 into q3 equal to 0. Now you solve this equation directly in a calci. So 3 you can get q1 as 7.69 into 10 raised to minus 6 mm, q2 is 0.104 mm and q3 is 2.73 into 10 raised to minus 6 mm. So you can have, here you can get doubt, what is that? At node 1 and node 3 actually it is fixed, right? Then the nodal displacement is there is no displacement, but here when we calculated we got this value. But you can observe here the value, the magnitude of this nodal displacement node 1 and 3, it is almost negligible because 7.69 into 10 raised to minus 6, that is 0.005 times of 0.76, that is almost, it's negligible. So but in case of Gaussian elimination approach we taken directly as 0, but here we are going to calculate that. So having, because it's not completely 0, having some displacement will be there, so that's why penalty approach will give the accurate result than the elimination approach. Almost penalty approach they will going to use in a computer software. So in FEA all packages too they are going to use penalty approach, because compared to the elimination approach this will give the better result. Finally we need to find the stress as usual, E1 into epsilon 1 is the B1 into Q, B1 is nothing but E1 by 1 by L1 minus 1, Q nothing but Q1 and Q2. Substitute all the values, you know well this one, so you are very familiar. So sigma 1 become 26.09 plus, that is why it's tensile. Similarly sigma 2 become E2 into epsilon 2, that is you will get around sigma 2 minus 20.8 minus, this is under section 2 under compression, section 1 under tension. And finally we need to calculate the reaction. So I told reaction we need to calculate like this here. At nodes 1 and node 3 fixed, therefore node 1 the reaction 1 is minus C into Q1 minus A1. Anyway A1 is 0, therefore minus C into Q1. Substitute the Q1 value, we already calculated that, therefore R1 will be this much, minus 73597.44, and also R2 will be minus C into Q3 minus A3, R3, this is not R2, R3, therefore A3 is 0, minus C3 into Q3, Q3 substitute the value, therefore we get 26219.09, 26219.09. Okay, fine. Now we will validate the result. See now 73597 plus 73597.4 plus 26.219 If you add it, you will get approximately 99, right? So that is equal to 100 into 10 raised to 3. Applied force equal to what we got? Reaction. Therefore, right. Problem is right. So this completes the problem on this penalty approach.